We're now going to turn to the case of interacting electrons in Thomas Fermi theory. When we do this, we're going to gain two new terms in the energy. As we saw for the uniform electron gas, we're going to get a classical electrostatic term, the Hartree energy, and an exchange term. The Hartree energy is easy to write down, so let's just do that. We have a half times the double integral over the two positions dr and dr prime of rho of r prime over 4 pi epsilon naught r minus r prime. That's absolutely standard electrostatics. Now we turn to the exchange energy. When we considered the uniform electron gas, we saw that the term epsilon x, which is the exchange energy per electron, could be written as follows: minus beta e squared over 4 pi epsilon naught, and then we have a rho of r to the 1/3. Though of course in the uniform electron gas, rho has no position dependence. The constant beta is simply 3/4 of 3 over pi to the 1/3. In order to convert from an exchange energy per electron to an exchange energy density, we're going to want to multiply by rho, because then we've got an energy per electron multiplied by electrons per cubic whatever, let's say angstrom, and that gives us an exchange energy density, which we will then proceed to integrate in order to give us a total energy. It's minus beta e squared over 4 pi epsilon naught rho of r to the 4/3. And the way that we calculate the total energy, as I've just alluded to, is as we did with the kinetic energy for the non-interacting gas, we integrate over the whole system. So we write that the total exchange energy is given by the integral dr of the exchange energy density, minus beta e squared over 4 pi epsilon naught rho of r to the 4/3. That then gives us a complete total energy for the system, so let's write that out. We have E total is equal to alpha h bar squared over m times the integral dr rho of r to the 5/3, that's the kinetic energy term, plus integral dr v of r rho of r, that's the interaction between the electrons and the nuclei. We have an e squared over 8 pi epsilon naught double integral dr prime of rho of r prime divided by r minus r prime, that's the Hartree energy, minus beta e squared over 4 pi epsilon naught integral dr of rho of r to the 4/3, which is the exchange energy. Now, we want to find the ground state, and we want to find the charge density, the electron density that corresponds to the ground state. We're going to do that by minimizing the energy with respect to the density. And so if we consider only first order variations in the energy at the minimum, we can write the following condition. We would say that 0 is equal to delta E tot, but then remember we have to constrain the number of electrons, and we have minus mu delta n. That's exactly as we saw for the non-interacting gas. Now, if we use the theory of functionals again, as we alluded to in the previous video, then we find the following. We see that 0 is equal to 5/3 alpha h bar squared over m integral dr of rho of r to the 2/3 plus the integral dr of v of r minus mu delta rho of r. Oh, I've missed a delta rho here. I'm just going to stick that in there. There's a delta rho of r here. Sorry about that. Plus e squared over 4 pi epsilon naught single integral, oh no, actually it's a double integral, I do beg your pardon, of, with respect to dr and dr prime, of rho of r prime delta rho of r divided by r minus r prime, that's the electrostatic, minus 4 beta E squared over 12 pi epsilon naught integral rho to the 1/3. That's a bit messy and I need to put a rho of r. Let me just change that. This is rho of r to the 1/3 delta rho of r dr. We can simplify that expression by defining some potentials. So we're going to define the following useful potentials. The Hartree potential is just the integral dr prime, and this is a potential as a function of r, of rho of r prime over 4 pi epsilon naught r minus r prime. That's an absolutely standard definition. And the exchange potential, Vx of r, is given by minus 4 beta E squared over 12 pi epsilon naught rho of r to the 1/3. Having done that, we can rewrite our condition as follows. We can say it's 5/3 alpha h bar squared over m rho of r to the 2/3 plus, I'm going to put the potentials all in one bracket, V of r plus V Hartree of r plus V exchange of r must equal mu. We can actually simplify this even further by lumping together all of these potential terms into what's known as an effective potential, V effective of r. And if we do that, then we see the following. We see that we have 5/3 alpha h bar squared over m rho of r to the 2/3 plus V effective of r must equal mu. Now this equation actually is quite remarkable. What it tells us is that there's an equivalence between the non-interacting electron gas in a potential V effective I'm going to put the 3 lines vertically to indicate that that's an equivalence. So the non-interacting electron gas in a potential V effective is exactly equivalent to, or the condition for the ground state is exactly equivalent to, the interacting electron gas in the potential V of r. This is a key idea which is exploited within density functional theory. So we can take an interacting electron picture and map it onto a non-interacting electron picture by changing the effective potential in which the electrons move. It's an extremely important concept, so do please spend a little while just thinking about that. And the two solutions will give you the same ground state. And I don't need to suggest that actually the non-interacting electron gas is considerably easier to solve than the interacting electron gas. However, do also note that we've introduced another layer of complexity. V effective of r depends on rho of r. So we need some kind of input, which in density functional calculations is generally given by a superposition of atomic densities. And we need a self-consistency cycle where we iterate backwards and forwards between the input charge density and the output charge density. So you can imagine you have an input charge density, you solve that to find the ground state, which gives you a different output density. Somehow you then transform that and you go round in a circle until you converge to a density and a potential that are consistent. So that ends the lectures on Thomas Fermi theory. Next we will turn to density functional theory.